Hello, this is Dr. Hanaa Assil, and this is Unit 5 of October 2023. This is in the Pearson Edexcel International A-Level Chemistry. So let's take a look at the first question. It says, which of these is a D block element but is not a transition element? Of course, you should know that a D block element means an element in that middle area of the periodic table, in which the last electron goes into a D orbital. But a transition element is a D block element that forms one or more stable ions with incomplete D orbitals. So we want stable ions with incomplete D orbitals, then that is regarded as a transition element. So let's take a look at cobalt. Cobalt originally is 27, so that's 4s2 3d7. If it forms a stable ion like +2, this still has incomplete 3d orbitals. Remember that when we remove electrons, we remove from the 4s first. Copper 29 is 4s1 3d10. When it forms copper 2+, then we remove one electron from the s, one electron from the d, so it has incomplete d orbital, so it is a transition element. Nickel is 28 4s2 3d8. If we form a 2+, then I still have incomplete d orbitals. But what about zinc? Zinc is 30. It has 4s2 3d10. Now, when it forms the stable +2 ion, that means we remove the electrons in the 4s. Well, the 3d is still complete, so we do not regard the zinc as a transition element. In which of these pairs does the transition metal have the same oxidation number? Well, let's calculate the oxidation number. You should be able to calculate oxidation number of each. So chromium in that first species, we don't know what it is. Each oxygen is -2, so the two oxygens are -4. Each chlorine is -1, so I have two of them, so that's -2, and the overall is 0. Calculating for the oxidation number of chromium, in that case, it comes out to be +6. Now, in the other species, there is an overall charge of +1. So that means the oxidation number of chromium plus ammonia, which is 0. Ammonia doesn't have any charge on it. I have two chlorines, each one, or two chlorides actually, each one is -1. So the overall has to be +1, and that means chromium is +3. Now we're looking for transition metals having the same oxidation number. If you do the same for B, the first one is +1, the other one is +2. In C, +3 and +4, but in D, both the vanadiums in these species have the same oxidation number of +5. What is the coordination number of chromium in this complex ion? Remember, what do we mean by coordination number? Coordination number is the number of dative bonds that are made with the central metal ion. Now, one of these ligands is bidentate, but the total number of dative bonds that are made to the chromium is 6. So that is the coordination number. Aqueous sodium hydroxide and aqueous ammonia are added until they are in excess to separate portions of a pale green solution. Now, when we added sodium hydroxide to it, it gave green precipitate. No further change, that means insoluble, in excess. And when we added aqueous ammonia, it gave also a green precipitate, but with excess, it dissolves to form a pale blue solution. And the question is, which of these is E? Now, if we look at the options that we have, first of all, the copper 2+ is blue, and they're saying it's a pale green solution that I'm starting with. So the copper ions originally are blue. They don't form green precipitate with sodium hydroxide or with ammonia. So it is not copper 2+. What about iron? Well, iron forms 2+, green solution. So I could be starting with a green solution. And when I add sodium hydroxide, it would give me a green precipitate with no further change. But remember that the iron 2 with ammonia, also the green precipitate does not dissolve. So when the question says green precipitate dissolves to form a pale blue, it's not iron 2. That's not iron 2. But what about nickel? Well, nickel as a solution is green. That's correct. And then if I put sodium hydroxide, remember vanadium is not green. So vanadium is not an option. In vanadium 2+, it's purple. Vanadium 3+ is the one that's green. So it's not vanadium. So let's look at nickel. Nickel 2+ as a solution is green. Now, what if I put sodium hydroxide? It would give a green or a gray-green precipitate. What about if I add aqueous ammonia? It would give a green precipitate that dissolves to form a pale blue solution. So this is what we're talking about. Okay. A small amount of aqueous ammonia is added to an aqueous solution containing zinc ions. A white precipitate forms. Which is the equation for this reaction? Remember that with zinc, if we add a small amount of ammonia, it would form a white precipitate. And with excess ammonia, we form the white precipitate dissolves to give a colorless solution. Remember that with ammonia, it acts as a base, so there is deprotonation at the beginning. And with excess ammonia, there is ligand exchange, so some of the water is replaced with ammonia. So what is the equation for the formation of the white precipitate? You should realize that that is my equation, in which I'm starting with zinc with 6 water ligands. If I put ammonia, so a small amount of aqueous ammonia, so I'm going to add 2 ammonia, not 4 ammonia. And then, so my choice actually is A or B, and then I'm getting a precipitate, and you should know that the precipitate should not have a charge. So it shouldn't be A. My product doesn't have a charge. So the answer is B. Acidified manganate ions react with ethane dioate ions, and this is the equation. The rate of the reaction increases at the beginning and then decreases. What are the reasons for these changes in rate of reaction? Remember that this reaction forms manganese 2+. And in this kind of reaction, you should realize, since as it forms the manganese 2+, the rate increases, that means the manganese 2+ acts as a catalyst. And if it acts as a catalyst, then the concentration later on would decrease. So at the beginning it increases because of the formation of manganese 2+. But then the rate decreases after that because the reactants are being used up. No more manganate. So concentration of reactants decreases. E cell is directly proportional to what? You should know that E cell, we said delta S total is R ln K. And then the E cell is proportional to ln K, and that means it is proportional to delta S total. So the E cell is directly proportional to delta S total and natural log of K. Standard electrode potentials can also be given an alternative name. The electrochemical series lists standard electrode potentials in order. Which of these is correct? First of all, what is the alternative name for the standard electrode potentials? Remember that the list that you have here in the data booklet, for example, is a list of the reduction potentials. So this is the standard electrochemical series, is a list of the standard reduction potentials. These are the reduction potentials, and the order of the standard electrode potentials in the electrochemical series, remember that the ones on top are the ones that have a negative reduction potential. These are the ones that are better reducing agents, more likely to lose than to gain electrons. And the ones down are the ones that are more easily reduced and tend to gain electrons. So this is a list of the standard reduction potentials, and the order is from most negative to the most positive. The half equation for the reaction taking place at the positive electrode in the alkaline hydrogen-oxygen fuel cell is this. What is the half equation taking place at the negative electrode? You have to remember the equations that happen in the hydrogen-oxygen fuel cell. And we said we could either have it in alkaline electrolyte or in acidic electrolyte. In both cases, the overall reaction that happens is hydrogen plus oxygen to give water. But the difference is what happens at the anode. At the anode, if we have, and remember that the anode is the negative electrode, and if we're talking about alkaline, then this is the reaction that happens at the anode, which is the negative electrode. The EMF of a cell is plus 0.57. The numerical value of the standard electrode potentials of the two half cells are 0.17 and 0.4. What are the signs of the standard electrode potentials of the right hand half cell and the left hand half cell? So we should know that the E cell is overall either addition of E oxidation plus E reduction, or if we're looking at the right hand side and the left hand side, it is the E of the right hand side minus the E of the left hand side, or if we're looking at our numbers, then it is negative of the left hand side plus positive of the right hand side. This gives a total of 0.57, and that is correct. An electrochemical cell is set up. Half cell is made from a piece of zinc and solution of zinc chloride. The second half cell is made from a piece of metal G and a solution of its G chloride. The two half cells are connected and a current allowed to pass. The zinc electrode increased by 0.635 grams. And the electrode of metal G decreased in mass by 0.6075 grams, and we're asked what is G. Remember that the number of moles, if we have zinc chloride and GCl2, so if we write an equation, the number of moles of one would be the same as the number of moles of the other. So if we say that the zinc lost mass by 1.635, that means the number of moles of zinc that reacted is 0.025 mole. We should get the same number of moles of G, and we can use that to get the molecular mass of G. So the molecular mass is mass over number of moles. This gives me a molecular mass of 24.3. Now, which of these choices has a mass number of 24.3? That is magnesium. Which of these is the weakest base? You should remember that when we have amines, the strength of the base depends on the availability of the lone pair of electrons on the nitrogen. Now, if we have ammonia, ammonia is a base, the nitrogen has lone pair of electrons that can be used to make dative bonds with H+. Now, compared to that, what about butyl amine or ethyl amine? You should realize that these are even more basic than ammonia, because the presence of the alkyl groups, butyl or ethyl, we call them electron donating. Electron donating means they make the lone pair of electrons on the nitrogen more available for making a dative bond, so they are more basic than ammonia. But if we look at phenylamine, you should realize that the lone pair of electrons on the nitrogen overlap with the electron cloud in the benzene ring, so that makes that lone pair of electrons on the nitrogen, they're not really available to make a dative bond with H+, so this would be the weakest base in that list. The amino acid 2-aminopropanoic acid exists as a Zwitter ion. Remember, all amino acids exist in around neutral pH. They exist as a Zwitter ion. That means that the NH2 is in the form of NH3+, and the acid part is in the form of COO-. Now, what will be the structure at pH 9? You should remember, at higher pHs, or in presence of alkali, then the amine part is in the form of NH2 and the acid part is in the form of the salt. So this is COO-. If we were to put it in acidic medium, then the NH3+, the amine part would be in the form of NH3+, and the acid part would be COOH. So here we're talking about pH 9. pH 9 means the amino part, the NH2 is NH2, and the acid part is in the form of COO-. An organic compound J reacts with sodium hydroxide to form ionic compound, hydrogen in presence of nickel catalyst, ethanol in presence of sulfuric acid. Which of these could be the structure of J? Let's take this one by one. We want something that reacts with a base to form an ionic compound. Well, that means that I must have an acid part, a COOH part, that reacts with a base to form the sodium salt. So B is wrong and C is wrong. So my choices are A or D. Now, we are told that the compound reacts with hydrogen in presence of nickel. Hydrogen in presence of nickel, that means it must have a double bond. This is hydrogenation of alkenes. So we want something that has a double bond and an acid part. And then we're told it reacts with ethanol in presence of sulfuric acid. Of course, if it is an acid group reacting with an alcohol in presence of sulfuric acid as a catalyst, this gives an ester. So we need acid and alkene, so that is choice A. A reaction scheme for the preparation of an azo dye is shown. So this is a scheme that we're given, and then we're going to be asked questions about it. So the first question is, step 1 takes place using a mixture of concentrated nitric acid and concentrated sulfuric acid at 55 degrees Celsius. Which one was step 1? This was step 1, where we reacted benzene with something to put a nitro group on the benzene. And we know that in order to put a nitro group on the benzene, we should put concentrated nitric and concentrated sulfuric acid. Now, we are told that it should be done at 55 and not at a higher temperature. Why is that? Remember that if we do this at a higher temperature, then we will have more and more substitution by nitro groups. So instead of just putting one nitro, we can put 2 nitros, 3 nitros on the benzene. So this happens at a higher temperature. We don't do that if we just want one nitro group substituting on the benzene ring. How is step 2 carried out? So this is step 2. Step 2, change the nitro group to amino group. How do we change nitrobenzene to what we call phenylamine? Of course, we do this using tin in concentrated HCl and then sodium hydroxide. So tin in concentrated, not dilute, and then sodium hydroxide. We change the nitro group to an amino group on the benzene ring. Step 3 takes place using sodium nitrite and dilute hydrochloric acid. This was step 3. So we had the phenylamine, we're adding sodium nitrite and dilute hydrochloric acid at 5 degrees Celsius, and we said this forms what? You should know that this forms the diazonium salt. Now, what is the structure of the diazonium salt? Of course, diazonium salt is something that has a triple bond between the nitrogens, so C and D are wrong. And then, because then the nitrogen will have 4 bonds, so we have a positive on the nitrogen that has a total of 4 bonds. So this is the diazonium salt that is formed when we react phenylamine with sodium nitrite and dilute HCl. And we said that this reaction has to be done at a temperature lower than 10 degrees Celsius, because any higher temperature would cause that product, the diazonium salt, to decompose. Okay, then step 4. Which one was step 4? This was step 4, where we have the diazonium salt and we want to make that azo dye, and of course we're going to react that with phenol in presence of what? You should realize that diazonium salt with phenol, in order to form that product, we should do it in alkaline medium in presence of something like sodium hydroxide. 10 centimeter cube mixture of methane and argon is ignited. The methane requires 4 centimeter cubed of oxygen for complete combustion. What is the volume of argon? So basically we have methane, we're burning it in oxygen. Of course, this is complete combustion, so this gives carbon dioxide plus water, and we should write the balanced equation. So this is the balanced equation. Remember, all of these are gases, so when we talk about gases, then the relative volumes can be used directly from the coefficients. So this volume of methane, if we have 4 centimeter cubed of oxygen, then what would be the volume of methane? These are 2 gases, so we can relate them directly. So 4 centimeter cubed of oxygen will need half of that of methane. So the volume of methane is 2 centimeter cubed. If I started with a mixture that has 10, that means the rest of it is the argon, which is 8 centimeter cubed. When 10 centimeter cubed of but1ene is ignited with excess oxygen, there is an overall decrease in volume of x centimeter cubed. We are given the equation, and then we're told a further decrease of y centimeter cubed takes place on addition of aqueous sodium hydroxide as carbon dioxide is removed. What are the values of x and y? So we have this equation. And what are we told? We're told that we're starting with 10 centimeter cubed of but1ene. So I'm starting with 10 centimeter cubed of but1ene. That would need how much of oxygen? It would need 60 of oxygen. And it will produce how much of CO2? It will produce 40, based on the coefficients in the equation. And then, what are we told? The question says, when 10 centimeter cubed of but1ene is ignited, there is an overall decrease in volume of x centimeter cubed. We started with a total of 10 plus 60, that's 70. We're forming 40, and that means the difference is 30. So the x is 30. Now, what is y? Y is the amount of CO2 that comes out, and we said that would be 40 centimeter cubed. This question is about electrochemical cells and redox reactions. Draw a label diagram of the apparatus you would use to measure the standard electrode potential of a copper 2 plus copper electrode with a standard hydrogen electrode, and include essential conditions. You should be able to draw this. The hydrogen half cell has hydrogen gas coming in on the right there at 298 Kelvin and 100 kilopascal. And then it is dipped into a solution of 1 mole per decimeter cubed of acid, like sulfuric or HCl. On the other half cell, we said we're trying to measure the standard electropotential of what? We have copper ions, and the copper ions in the solution should have a concentration of 1 mole per decimeter cubed. And we need a copper electrode, and of course all of this is connected with a wire that has a voltmeter, and the solutions are connected by a salt bridge, which is usually saturated potassium nitrate solution. We should be able to draw this diagram of the apparatus used to determine the electrode potential of any half cell with respect to hydrogen standard electrode. The standard electropotentials for two half cells are shown. Explain in terms of electrode potentials why acidified dichromate ions react with concentrated hydrochloric acid to form chlorine, even though the E cell is minus 0.03 volts. So let us take a look. The key point is that we're adding concentrated hydrochloric acid, and that means I'm increasing the H plus ions. And when we increase the H plus ions in that first equation, the point of equilibrium shifts to the right. And that means the E naught of that first equation increases a little bit. Now, if we're adding concentrated HCl, that means also the chloride ions increase. So the point of equilibrium in the second equation shifts to the left. And the E naught of that equation decreases a little bit. So the overall total E cell will become positive. Write the cell diagram using conventional representation of half cells for the reaction to produce chlorine. Where is the reaction to produce chlorine? What are we doing? We're doing the dichromate going to the chromium 3 plus and the chlorine. So we have the dichromate going to chromium 3 plus, and then the second equation has to be inverted because we're trying to make chlorine. So this is chloride going to chlorine, and when we invert an equation, we invert the sign of the E naught for that equation. Now, how do we write the cell diagram? We start with oxidation on the left. So in the oxidation, which one is oxidation? It's the chloride going to the chlorine. And this is a mixture of solution and gas, so the electrode will be platinum. So we have platinum on the left. This is where we have oxidation. Remember, we start the cell diagram on the left with the oxidation part. And then the double lines there represent the salt bridge. And then we have the part where we had the reduction, the Cr2O7 2 minus with 14H plus becoming 2Cr3 plus and 7 water. And also these are a mixture of solutions, so our electrodes in that half cell is also platinum. So this is the cell diagram for that reaction. When 25 centimeter cubed of a 0.1 mole per decimeter cube solution of X2O5 reacts with a reducing agent, X is reduced to a lower oxidation state. To oxidize X back to its original oxidation state required 50 centimeter cubed of 0.02 mole per decimeter cubed acidified potassium permanganate solution. And we're given the half equation for this reaction. Calculate the oxidation state of X after it has been reduced. So we're starting with X2O5. We can tell the oxidation number in X2O5. Each oxygen is -2, so that is a total of -10 for the oxygens. That means the two X's are +10, and that means oxidation number of X is +5. And then we're given the number of moles of permanganate. We can get number of moles of permanganate, concentration times volume. Of course, the volume divided by 1000. So this gives 0.001 mole. and the number of moles of the X2O5 that reacted with it, we have 25 centimeter cubed of 0.1, so this gives number of moles 0.0025. Now, 1 mole of the X2O5 will give twice the number of moles of X. So if I'm looking for the number of moles of X, it is twice the number of moles of the X2O5. So now I have number of moles of X and number of moles of the manganate that reacts with it, and obviously the 1 mole of the manganate reacts with 5 moles of X. If we divide through by 0.001, this means 1 mole of manganate, and you should realize that 1 mole of manganate has 5 moles of electrons. It reacts with 5 moles of X, and that means if we have 1 mole of manganate, it reduces the oxidation number of X by 1, so from +5 to +4. This question is about compounds and complex ions of iron, and we're given first of all the percentage by mass of a compound of iron, and we're told to calculate the empirical formula. You should remember how to calculate empirical formula. We said we have these elements, we're given a certain percentage. The first thing we do is divide by the mass number of each one, and the numbers that come out, we need to simplify the number of moles that come out, so we divide by the smallest, determine which one is the smallest. This gives these ratios, and that means the empirical formula is K2FeO4. The reaction between iodide ions and persulfate ions is thermodynamically feasible under standard conditions. The reaction is very slow, but is catalyzed by the presence of iron 2 ions. Remember that we use this as an example for homogeneous catalysis, in which we have all of them in the aqueous medium and the catalyst is in the same phase as the reactants. Give a reason why the activation energy for this reaction is high in absence of a catalyst. Why is this originally a very slow reaction? You should remember that this is because the reactants are both negatively charged ions, so trying to bring them together in order to react is difficult since they will repel each other. Write the ionic equation for the reactions that occur when the catalyst is added. You should realize that when we add iron 2+, it reacts with one of the reactants to give iron 3+, and then the iron 3+ reacts with the iodide to regenerate the iron 2+ again. So remember that these are the two equations for the catalysis of this reaction. In aqueous solution, iron 2 exists as this complex ion. Explain how water acts as a monodentate ligand. Remember that water is a monodentate ligand. That means each molecule forms one dative bond to the central ion. This is because the oxygen has lone pair of electrons that can be used to form a dative bond to the central metal ion. Explain the shape of this complex ion. Remember that if we have 6 ligands, we have this kind of octahedral structure. So this is for minimum repulsion between the 6 shared pairs of electrons with the 6 ligands. Hemoglobin is an iron 2 complex which carries oxygen around the body. Part of the structure of oxyhemoglobin is shown. The 4 nitrogen atoms are part of a multidentate ligand in the heme group. Explain in terms of the iron 2 complex why carbon monoxide is toxic. Remember that if carbon monoxide is attached to the hemoglobin, this forms what we call carboxyhemoglobin. And the problem is the carbon monoxide in that case has replaced the oxygen. So instead of the iron 2 plus bonding to oxygen, it's now bonded to carbon monoxide. And this dative bond that is formed with the carbon monoxide is actually stronger than the dative bond formed with oxygen. So the carbon monoxide binds more strongly to the iron 2, forms stronger dative bonds that are harder to break, and that means less hemoglobin transports oxygen to body cells. Ethane dioweight ligands react with iron 2 ions in aqueous solution. Explain in terms of entropy why this reaction is feasible. Remember, when we talk about entropy, what do we talk about? We talk about increase in number of moles. So we started with 3 moles and we ended up with 5 moles in the products. So there is an increase in the number of moles, and that means the delta S system is positive and the reaction is thermodynamically feasible. Potassium dichromate oxidizes iron 2 ions to iron 3. Iron 3 ions do not react with acidified potassium dichromate. A solution Y contains this amount of iron as a mixture of iron 2 and iron 3. 50 centimeter cubed of sulfuric acid is added to 25 centimeter cubed of Y. It is titrated with a solution containing this amount of dichromate ions, and the titration is repeated until concordant results, and we got a mean titer of 22.55. Calculate the percentage of iron represented as iron 3 in Y. So we're told that Y is a mixture of iron 3 and iron 2, and the iron 2 reacts, the iron 3 does not. So we can first get the number of moles of dichromate. So the number of moles of dichromate, we are told that we have 2.56 grams per decimeter cubed. So we can change that to moles, mass over the molecular mass of the dichromate. So this is the number of moles. Then we can get, we used only what? We used 22.55. So we can get the number of moles in that volume. So that is the number of moles of the dichromate used. And that means the number of moles of iron 2 plus from the equation up there. You can see that dichromate reacts with 6 moles of iron 2. That means number of moles of iron 2 is 6 times the number of moles that we calculated for the dichromate. Then that is in 25 centimeter cubed that we did in the titration. But I want number of moles in a decimeter cubed, so we multiply by 1,000. This is number of moles in 25, so how much in 1,000? So actually you multiply by 1,000 divided by 25. This gives me the number of moles per decimeter cubed of iron 2 plus. And that means I can get the mass of the iron 2 plus, the number of moles calculated times MR of iron. So that means I have 3.58 grams of iron 2 plus. Now that means the percentage in Y, remember he says up there that we had a mass of 6.28 grams per decimeter cubed of Y. So I can use the mass of iron 2 plus. This is from the mixture, but we're looking for iron 3 plus. So that would be the difference over the total times 100. And that means I have 43% of the mixture is iron 3 plus. This question is about benzene and some of its compounds. Benzene reacts with bromine in presence of iron 3 bromide catalyst to form bromobenzene. Draw the mechanism for this reaction, including the formation of the electrophile. So, how do we draw this? Remember, the electrophile is formed from reaction of bromine with the iron 3 bromide. This is then attacked by the electrons from the benzene ring, placing a bromine on one of the carbons, but we have a positive charge in the benzene ring, and the electrons that are bonded to the hydrogen are used to remove the positive charge in the benzene ring and form the bromobenzene. Of course, the other products are HBr, and the iron 3 bromide is regenerated. Please learn this mechanism. Compare and contrast the reaction of benzene with bromine with the reactions of cyclohexene with bromine and phenol with bromine. Include reasons for any differences. Detailed mechanisms are not required. So basically we're comparing between the reactions of benzene, cyclohexene, phenol with bromine. So we should know that benzene, we have the pi cloud that is delocalized to form stable and electron cloud. This happens in benzene and in phenol actually, so they both undergo what we call electrophilic substitution. In benzene, the delocalized electron ring is very stable, so a catalyst is needed for the reaction with bromine. We said we need iron 3 bromide as a catalyst. But in phenol, the reaction is faster. That is, phenol is more reactive. This is because in phenol, the lone pair of electrons in the oxygen overlap with the delocalized pi cloud of the benzene ring. This increases the electron density of the ring and makes it more susceptible to do electrophilic substitution. In cyclohexene, we don't have that. In cyclohexene, the pi electrons of the double bond are not delocalized, so this undergoes electrophilic addition, and this occurs at room temperature. It is fast, and this forms 1,2-dibromocyclohexane. Devise a synthesis to convert bromobenzene to benzamide. Include reagents, conditions, structures of the intermediate compound. So we're starting with bromobenzene. What do? We can do this. We're trying to add an extra carbon on the benzene ring, so we can go through Grignard reagent. So the first thing we do is add magnesium in dry ether. This forms the Grignard reagent that can then be reacted with carbon dioxide and HCl to give the carboxylic acid on the benzene ring. Now I can then do a PCl5. This will change it into the acyl chloride. Add ammonia. This gives the benzamide, which is the required product. Semi-aromatic polyamides have high melting temperatures, high strength and rigidity, and are resistant to chemical attacks, so they have many applications in engineering. Draw the repeat unit of the polyamide formed from the monomers shown. So basically we have monomers. We're trying to join them to make polymers. These are a diacyl and a diamine. So we remove the chlorines from the diacyl compound, we remove H's from the amine, and we join them together. So this would be the structure of the polymer. Okay. Explain why polyamides have higher melting temperatures than polyalkenes. Polyamides are compounds that have C double bond O and NH, and these can form hydrogen bonding with each other. So in between these molecules we have hydrogen bonding which are stronger than the London dispersion forces that are between the polyalkenes. So polyamides have intermolecular hydrogen bonds. These are stronger than the London forces that are present between molecules of polyalkenes. This needs more energy to be broken. Salicylic acid, we're talking about salicylic acid, and we're told salicine was extracted from the bark of willow trees in the first half of the 19th century. About 30 years later, scientists showed that salicine was converted into salicylic acid in the body. Salicylic acid was given to patients with fevers and their symptoms were reduced. However, it caused severe irritation to the lining of the mouth, esophagus, and stomach because it's an acid. So we used in 1890s, Hoffman converted salicylic acid into acetyl salicylic acid, which is what we call aspirin, and is still used to treat fevers and used as a painkiller. Salicylic acid may also be converted into methyl salicylate. This is the active ingredient in oil of wintergreen, which is applied externally to treat joints and muscle pain. Now, the first question is, give the IUPAC name of salicylic acid. So how would we name this compound? This is 2-hydroxy benzene carboxylic acid, or you could say 2-hydroxy benzoic acid. So benzene with a COOH can be referred to as benzene carboxylic acid or benzoic acid. So this is 2-hydroxy benzoic acid. Acetyl salicylic acid is formed when salicylic acid reacts with ethanoic anhydride. Name the 3 functional groups in this compound. So this is acetyl salicylic acid. What functional groups do we have? You should realize that we have a carboxylic acid, we have an ester, and we have that benzene ring, which can be referred to as benzene or arene. Write the equation for the reaction of salicylic acid and ethanoic anhydride. We are told the formula of ethanoic anhydride, and we're told the formula of salicylic acid, and this is the product. We were told this is the product. So what is the other product? You should realize that the other product will be ethanoic acid, because the ethanoic anhydride has 2 of these groups of ethanoic acid bonded together. So my other product here is ethanoic acid. 2 grams of salicylic acid produced 74.8% yield of the acid. Calculate the mass of acetyl salicylic acid formed. This was the equation. And we're told that we started with 2 grams of salicylic acid. So I have to determine what is the theoretical yield that I should get. So number of moles of salicylic acid, mass over molecular mass, I get number of moles of what we started with. Now, from the equation, I should end up with the same number of moles of product. It's a 1-to-1 ratio. And that means that the mass I should get is 2.6 grams. But we're told that we got only 74.8% yield, and that means my actual mass obtained is 74% of that. So that is 1.95 grams. Acetyl salicylic acid is only slightly soluble in water. Complete the equation to show the dissociation of acetyl salicylic acid. Of course, this is an acid. It will break up to form COO minus and H plus. The dissociation of acetyl salicylic acid is different in the acidic conditions found in the stomach compared with the slightly alkaline conditions in the small intestine. Explain this difference in dissociation. Well, what was the equation? This was the equation, and that means if we are in acidic conditions, what happens to this equilibrium? In acidic medium, the equilibrium would shift to the left, so less dissociation of the acid. And in alkaline medium, the hydroxide ions react with the H+, so the H+ is being used up and the equilibrium would shift to the right, causing more dissociation. Identify by name or formula the reagent needed to convert salicylic acid into methyl salicylate. So I'm starting with salicylic acid. I want to change it into methyl salicylate. That means I am trying to make an ester using methanol. So the methanol would react with that acid group to form the methyl ester. The high-resolution proton NMR spectra of acetyl salicylic acid and methyl salicylate both contain 4 peaks from the protons on the benzene ring and 2 other peaks from the OH and the CH3 protons in the side chains. Complete the table to give the chemical shift ranges that you would expect for each type of proton on the side chain. So remember that we can look at the data booklet, and from that you can determine the chemical shifts expected for these kinds of protons. Acetyl salicylic acid in aspirin tablets is hydrolyzed by excess sodium hydroxide. The unreacted sodium hydroxide may be titrated with a standard solution of HCl to determine the percentage of acetyl salicylic acid in tablets. So we have tablets that have acetyl salicylic acid. We react with sodium hydroxide and the excess is titrated with HCl. So aspirin tablets can be analyzed using this procedure. Add 25 centimeter cubed of 1 mole per decimeter cube sodium hydroxide to a known mass of powdered aspirin tablets. Heat the mixture to hydrolyze the aspirin, so this reacts with the sodium hydroxide. Cool the mixture, and whatever is left, the rest of the sodium hydroxide that did not react, that is what is left in solution. Make the solution up to 250, mix thoroughly, pipette 25 centimeter cubed of that into a conical flask, titrate it against hydrochloric acid using phenolphthalein indicator. Repeat the titration until concordant values are obtained. And we're given that we started with 0.76 grams of aspirin, and when we titrated it with HCl, the titer was 16.95 centimeter cubed. Now, we repeated this with different brands of aspirin tablets, and these are the percentages of acetyl salicylic acid present. So the question is, the one that we used in the experiment, determine which brand was analyzed. So look at what we're given. We reacted sodium hydroxide and then the excess was titrated. So we did, and we got that the mean titer is 16.95 of acid. So I can get number of moles of acid, concentration times volume, and from the equation with sodium hydroxide, we know that's a 1-to-1 ratio. That means number of moles of sodium hydroxide in the 25 centimeter cube that was titrated is the same. And that means I can get the number of moles of unreacted sodium hydroxide in all of the 250. So that's the number of moles of unreacted sodium hydroxide. And then we were told that at the beginning we added 25 centimeter cubed of 1 mole per decimeter cubed of sodium hydroxide. So I can get the original number of moles of sodium hydroxide. And that means the difference between them would be the number of moles of sodium hydroxide that reacted. So now that I know the number of moles of sodium hydroxide that reacted, I can determine the number of moles of acetyl salicylic acid that was present. From the equation, it will be half the number of moles of sodium hydroxide that reacted. And we have the MR, so we can get the mass of the acetyl salicylic acid, number of moles times MR. So this is the mass that we got from the acetyl salicylic acid. Now we started with 0.76 grams of aspirin. That means according to our calculations, the brand of tablet that we used has 95.3% acetyl salicylic acid. I look at the table and that tells me that that means that we used aspirin B. Are we okay? Followed everything? Okay. I hope this was useful to you. Please continue studying. Share the video with your friends, and thank you for listening.